Simple alkyl halides are nearly tetrahedral, and so the carbon that the halogen is attached to is approximately sp3 hybridized. The bond between the carbon and the halogen is the overlap of an approximately sp3 carbon orbital overlapping with an orbital on the halogen. As you move down the group from fluorine to iodine, the principal quantum number for the orbital on the halogen varies from n equal 2 to n equal 5 for iodine. And correspondingly, we find the lengths of these bonds and the strengths of the bonds change. So carbon and fluorine form a very efficient overlap between their orbitals because they lie in the same row on the periodic table and their valence electrons are in the same principal quantum level. And as you move down the group, the efficiency of that overlap decreases because carbon's valence orbitals are in the n equal 2 valence shell, whereas, say, something like iodine's valence electrons are in n equal 5. And as a result, we get these long, relatively weak bonds. Alcohols can be considered organic derivatives of water. So where water has two hydrogens bonded to approximately sp3 hybridized oxygen, an alcohol replaces one of those hydrogens with an alkyl group of some sort. The electrons in an orbital near an electronegative oxygen atom are more stable than electrons near a carbon atom. And what we find is then that carbon-oxygen bonds are a little shorter and stronger than, say, typical carbon-carbon bonds. The structure is consistent with a tetrahedral electron pair geometry, and we see that the bond angle in alcohols is similar to that we see in tetrahedral compounds. Just as with carbon-oxygen bonds, we also find that carbon-nitrogen bonds are a little shorter than a typical carbon-carbon bond for the same reason that I mentioned before, and that is the electronegativity of the nitrogen, its effective nuclear charge, meaning the electrons near that nitrogen are a little bit more stable. As a result, the carbon-nitrogen bond is a little stronger, a little bit more stable than a carbon-carbon bond. But of course, nitrogen isn't quite as electronegative as oxygen, so the effect is a little smaller. In simple amines, the electron pair occupies the site of a fourth substituent in a pyramid. Simple amines are trigonal pyramidal because of the tetrahedral electron pair geometry. In principle, these structures are chiral. You can see here this would be an R N-methyl-1-propanamine. This is the S form over here. In reality, the barrier to inversion for this structure, where it kind of undergoes what's referred to as an umbrella flip, think of an umbrella blowing inside out in the wind, that barrier to inversion is quite low and easily is overcome by room temperature. So even at very low temperatures, you can't isolate typically the enantiomers of most simple amines. There are some examples of some types of amines, aziridines, which are three-membered rings that contain a nitrogen, for orbital reasons are somewhat resistant to this umbrella flip, and you can isolate enantiomers of those. But most simple amines rapidly racemize if you could isolate them. That barrier is only about 5 kilocalories per mole, well below the 20 or 30 kilocalories per mole available at room temperature. And so we generally think of these structures as rapidly interconverting between the two enantiomeric forms. Alkyl halides are quite polar compounds by virtue of the polarity of the carbon halogen bond. There are a couple different ways of depicting that polarity. Typically, the use of these polarity arrows is the way that one indicates the polarity of individual bonds. The notion here is the arrow points toward the somewhat negative end of the bond, and this represents a positive sign here. That's the positive end. It basically means slight positive charge, slight negative charge in that particular direction. That polarity gives low molecular weight alkyl halides, typically a polarity in the range of about 2 dBi. We measure polarity in dBis, and you can see that within error here, most methyl and ethyl halides have about the same polarity because of the polarity of those bonds. You can see also within the data, if you look at, say, for instance, just the methyl compounds within the data. So if we look at the methyl fluoride, methyl chloride, methyl bromide, and methyl iodide, you can see a slight decrease in polarity, and that's consistent with the decrease in electronegativity as you go down the group. But there is some other issues in here because it isn't just electronegativity, it's also the length of the bond that matters. And so the bond is getting longer as the electronegativity is dropping. In the condensed phase, alcohols form typically liquids under most conditions. And the reason for this is due to the attractive forces between the molecules. Alcohols are polar, so there are, of course, dipole-dipole interactions. But there's also polar oxygen-hydrogen bonds, and those polar oxygen-hydrogen bonds can give rise to hydrogen bonding, where the somewhat positive hydrogen of one alcohol is interacting with a lone pair of electrons on the oxygen of another, forming relatively strong intermolecular attractions known as hydrogen bonds. Hydrogen bonds typically have bond energies in the range of about 5 kilocalories per mole. That's enough to kind of keep the molecules in contact, but certainly not enough to form a covalent bond. So that ability to form hydrogen bonds results in even very low molecular weight alcohols like methanol having relatively high boiling points for that molecular weight. Methanol boils at 65 degrees, and then as the alkyl group gets larger and depending upon its shape, those boiling points correspondingly go up because you can then start getting van der Waals interactions between the alkyl chains. The other thing that we find with alcohols is that they are either miscible or very highly soluble in water. And that shouldn't be surprising, given that the alcohols can hydrogen bond with water molecules. We'll talk a little more about their behavior in water when we talked about their acid-base properties here in a minute. Amines can also form strong intermolecular forces, such as hydrogen bonding and dipole-dipole interactions. Just like alcohols, amines are polar. Nitrogen's more electronegative than carbon. And if you have a primary or secondary amine, or these compounds can form hydrogen bonded networks in a fashion that's similar to what we see in alcohols. And so again, as a result, you find for their molecular weights, you find relatively high boiling points for simple amines. And, you can see here that, for instance, methylamine has a higher boiling point than does ethane by quite a degree. If there are no hydrogens on the nitrogen and no ability to form hydrogen bonds, then we find correspondingly lower boiling points. An example of that would be here with trimethylamine. Alkyl halides are neither particularly acidic nor particularly basic, but alcohols and amines are a different thing. And so we need to talk a little bit about acid-base properties. As you know from studying water in general chemistry, water is a molecule that can act as both a Bronsted base and a Bronsted acid. Water is a Bronsted base by virtue of a lone pair on oxygen and can react with strong acids, accepting a proton from those acids to form a hydronium ion. Likewise, water can act as a Bronsted acid and donate a proton to strong bases, forming the conjugate base hydroxide. Well, alcohols are similar in that regard. They have an ability to demonstrate Bronsted basicity, again, because of the non-bonded pair of electrons on oxygen. They will react with strong acids in the same way that water does, can accept a proton, and they form species that look like this. In water, H3O plus is hydronium ion. If there's an alkyl group present, we refer to these species as oxonium ions. This has really important consequences in organic chemistry because there's a subsequent reaction that can occur, and which we're going to talk about at greater length later on in the course, and that is the ability to fragment this carbon-oxygen bond by the loss of water. It's a good leaving group, neutral molecule, to form carbocations. Simple alcohols don't do this on their own. We don't fragment the carbon-oxygen bond. Doing so results in the formation of both a cation and an anion, and energetically, that's typically a barrier that isn't overcome under normal conditions. But once the alcohol is acted as a base and is protonated, the loss of water now is a much lower energy process because one of the products of that reaction is a very stable neutral molecule water. And then depending upon the structure of this carbocation, that can be a reasonably stable carbocation that can form. So we're going to deal with this sort of reaction pathway and the fate of those carbocations later in the course. Alcohols, like water, can also behave as acids. And if a strong enough Bronsted base is employed, you can deprotonate alcohols, and the result of that are these negatively charged oxygen anions with alkyl groups attached to them, and generically these are called alkoxide ions. You want to think of alkoxide ions like this as simply organic derivatives of hydroxide, and they have a lot of the same properties as hydroxide do, being a strong Bronsted base. If you look more closely at the relative acidity of alcohols and compare them to water, you can see they're very, very similar. So if you look at the numbers here, water has a pK of 15.7 at room temperature, and alcohols are very close to that. But we do get some variation depending upon the nature of the alkyl group in the alcohol. You can see that there's just a slight variation going from methanol to ethanol, but branching results in some changes that are pretty significant here. It's important to remember here, these are pKa units, so we're basically talking about at least 1 or 1.5 pKa units. Remember, 1 pKa unit is a factor of 10, so T-butyl alcohol, for instance, is some 10 times less acidic than something like ethanol. And so it kind of begs the question, why do we see those differences even though those functional groups are very much the same? As is typical in organic chemistry, we really want to look at the nature of the conjugate base to understand acidity. So here we have T-butyl alcohol and methanol, and on the right-hand side, we can see their conjugate bases. So we're employing some strong base to deprotonate these. This is generically the conjugate acid of that strong base, but we really want to focus on the conjugate base over here and what it's doing in solution, because we measure pKa's in solvents of some sort, often water. And it wasn't known until about the 1970s why we saw these differences in pKa between things like methanol and T-butanol. But we now know the origin, and it has to do with the stability of these anions in the solution. It turns out that something like methanol, with a very small alkyl group, is strongly solvated. The solvent molecules can interact quite strongly with that negative charge, and that stabilizes it. And so it favors those energetics and makes it easier to form. The T-butyl group, because it's a large alkyl group, in a sense kind of keeps the solvent molecules away. It pushes them away. It makes it difficult for these solvent molecules to approach closely to that negative charge. And so this anion, while it's a negatively charged oxygen, because of the shape of the alkyl group, it's less well solvated and less stable in solution. And that disfavors the equilibrium, and as a result, T-butanol is slightly less acidic. So it's really not less acidic because of anything structurally different in the acid. It's less acidic because of the stability of the conjugate base anion in the solution that's formed. A little bit more about solvents. We're going to be dealing with their effects on reactions at various times throughout the course. Broadly speaking, we classify solvents in organic chemistry as either polar protic solvents or polar aprotic solvents. And there's a relatively simple difference between the two, and that difference is their ability to hydrogen bond. Protic solvents can hydrogen bond because they contain a positively polarized proton. Aprotic solvents do not hydrogen bond in that way. Nevertheless, we have reasons for employing both of these, but let's look a little more closely at what solvents are doing in solutions. First, here are some very common laboratory solvents. Water is sometimes used in organic chemistry, but less often than you would think. We have some protic solvents. You can see the categorization over here. These first four are categorized as protic, and they all contain an OH group in some form. So carboxylic acids have OH groups, alcohols have OH groups, and those are hydrogen bonding moieties. These other four solvents do not contain any OH or positively polarized hydrogen. We have dimethyl sulfoxide, acetonitrile, this is dimethylformamide, and nitromethane. And these are all solvents that are quite polar, but don't have hydrogens that can participate in hydrogen bonding. Here are dielectric constants for each of these. It's a measure of how well these solvents can separate charges, and you can see it varies quite a bit. It's largely a function of polarity. Water's the most polar compound in this list, but there's some other very polar compounds. Ethyl alcohol, for instance, is quite polar. If you consider the possible intermolecular interactions between polar solvents and, say, an ionic compound, then you can imagine solvent molecules surrounding the cation and solvent molecules surrounding the anion. In the case of protic solvents, here we have water surrounding sodium and chlorine. So we're looking at a saltwater solution and the interactions between water and the sodium cations and the chlorine anions. You can see that water would be attracted to positively charged sodium ions by virtue of the somewhat negatively charged oxygen atoms. This would be a dipole ion interaction. But water's interaction with chlorine should be much closer interaction because the positively polarized hydrogens can approach quite closely to chlorine. And so you get strong solvation of ions by water molecules. The other place that we see solvent interactions is that old adage of like dissolves like. And so, for instance, why do sucrose molecules dissolve so readily in water, table sugar, when we put that into a hot cup of tea? And the answer is because sucrose has functional groups that are very similar to water. Sucrose is actually covered in a bunch of alcohol groups. Alcohols, as I said before, are really nothing more than organic derivatives of water. And so you can get hydrogen bonding and you can get dipole-dipole interactions in the same way that water molecules interact. And the result is sucrose is very soluble in water. Lastly, we're going to talk a lot more about solvents later on in the course and throughout the course as we talk about different reactions and how certain solvents are suitable. Relatively nonpolar organic compounds, such as hydrocarbons, lack strong intermolecular forces of any kind, such as hydrogen bonding. So typically, they have very poor solubility in polar protic solvents. On the other hand, very polar organic compounds tend to be very soluble in polar protic solvents. Chapter 7, we'll talk more about how solvent choice and the medium in which you run a reaction can really greatly impact reactivity. The choice of wrong solvent for a particular reaction can have dire consequences.